Hi everybody. This video is going to be on section 7.8, Improper Integrals. So suppose we were asked to solve the following integral. Or let me put it this way, is the following valid? So let's say you were asked to integrate the integral from 0 to 3 of 1 over x minus 1 dx. So, you could look at this and you could say, well, the antiderivative is the natural log of x minus 1, right? And we're going from 0 to 3. And so this ends up being ln of 2 minus ln of 0 minus 1 is negative 1, but the absolute value of negative 1 is 1. And so you just get the natural log of 2. So question, is that valid? Well, I want you to think about what the graph of 1 over x minus 1 looks like. Doesn't 1 over x minus 1 actually have an asymptote at x equals 1? So it actually looks like this. And so what do we even mean when we write that integral down? Because normally that integral would be the area under a curve. And so what it looks like is that our area actually seems to go to infinity, right? We've got this point of discontinuity here. In fact, we've got an infinite discontinuity. So in fact, all of this is not valid. This is not correct. Okay? Why? So the fundamental theorem of calculus, part 2, says that the integral from a to b of f prime of x dx is equal to f of b minus f of a, right? That's what I tried to use above. However, there's a condition if f is continuous on a to b. So that's what we were missing above, right? The function that we just wrote down was not continuous on a to b because it had this infinite discontinuity right at 1. Okay, so we need to learn how to solve integrals like this. So that is what we talk about in this section amongst other things. So we will now learn how to solve what are called improper integrals. Integrals where the fundamental theorem of calculus, part 2, fail. Okay, so there are two types actually of improper integrals that we're going to learn about in this section. Okay, so what are the two types? So type 1, so let me write it this way. So type 1 is called infinite integrals. So let's do the definition here. A type 1 improper integral is a definite integral that has infinity as its upper limit or negative infinity as its lower limit. Or both. Okay, so this is not the kind of thing that we saw in my example that I wrote down before, okay? But what we're talking about is when we have an actual infinity in there, okay? So let me give you an example of what I mean. So I could write something like this down. Some constant to infinity of f of x dx. So question, what could we define something like this to mean? What does it mean to have an integral that goes to infinity? Let's try to clarify this using the concept of limits, okay? So the idea is, we know that this means area under a curve, right? However, what we're saying is that we actually want to find the area as we go to the right forever. So how would we quantify this? So this is actually going to equal the following. What we're going to do is instead of going to infinity, what we're going to do is we're going to go from a to t. And so what is t? T is just some variable. So let's say that t is over here. And let's say that a is over here. So if we do the integral from a to t, then that means we're actually talking about this area right here, right? But then we want t to get bigger and bigger, don't we? And so what we would do is we would write that this is the limit as t goes to infinity of that integral. Okay, so that is the definition of that integral. Likewise, so I'll say similarly, the integral from negative infinity until a constant a of f of x dx is going to be, you guessed it, we're going to do the limit as t goes to negative infinity of the integral from t to a of f of x dx. Okay, this is a similar picture, except we're actually going to the left forever, right? So if we were to draw this picture, it looks something like this, and then we're letting t go to the left forever, right? So that is this picture, and this is this picture right here. Okay? So let's write down a more formal definition here, because this leads us to some new terminology. So definition. If the limit exists and equals L, we say the integral converges to L. if the limit does not exist, we say the integral diverges. Okay. So again, let's go back to our picture, okay? Whenever you write down a limit, it may not exist, right? So when you calculate a limit, we're well aware that sometimes you get an answer that makes sense. Other times the limit might go to infinity or it just doesn't exist, right? And so if either of those is true, if it's infinity or does not exist, we say that it diverges. The only time it converges is if the limit actually equals a number. So the next thing. What if our integral goes from negative infinity to infinity? Okay. So let's write that down. You might have something like this. Okay, so it turns out that what you can do is you can instead actually write it out this way. Let me write this instead. So in case you're wondering, this is weird. How can I integrate from negative infinity to infinity? Well, the reality is all you do is you split it up into two pieces, okay? And you know how to do each of these pieces because each of these pieces is the ones that we just discovered or the ones that we just discussed in the previous one, right? So what we would do is we would say if both integrals on the right side converge, then so does the left. And it converges to their sum. Okay, that is what this statement I just wrote means. So in other words, if this converges and this converges, then you can say that this guy converges also. However, if either one on the right diverges, then so does the integral on the left. Okay, so what that means is that the only way that the integral on the left can converge is if both integrals on the right do. If either one doesn't, then you can say that the one on the left does not either. Okay? So because this involves taking limits, I want to remind you guys of something before we do some examples. So don't forget L'Hopital's rule. What does L'Hopital's rule say? It says that if you're taking a limit if you get 0 over 0 or some infinity over some other infinity, then this limit can be calculated by instead taking the derivative of the numerator and denominator. Okay, this is what L'Hopital's rule says, and I wanted to remind you guys because anytime that you take limits, you may have to use L'Hopital's rule to solve the problem. Okay? All right, let's do some examples. Example 1. We're going to do the limit, not limit. We're going to integrate from 0 to infinity of 1 over the 4th root of 1 plus x dx. Okay, so remember the definition, guys. This equals, and I want you to get used to writing this, okay? We're always going to write the limit definition. It's the limit as t goes to infinity, and then we're integrating from 0 to t of 1 over the 4th root of 1 plus x dx. Okay, so now we are able to use the fundamental theorem of calculus part 2 on the right side. Okay, because now we're going from 0 to t, and then we're just taking a limit at the very end. Okay, so we need to figure out what the integral of 1 over the 4th root of 1 plus x is. So let's go ahead and do this integral down here. What is the integral? Now I'm doing this guy. And I'm going to integrate from 0 to t. So in other words, what I'm doing is just this part. I'm doing it over here. So what would that integral be? How would I integrate that? Well, don't forget that that's really 1 plus x to the negative 1/4, right? And so how would you take that antiderivative? You can add 1 to that, that's 3/4, and then that's going to become 4/3 times 1 plus x to the 3/4, and we're going from 0 to t, and then we can plug in t, and then we can plug in 0, what's that equal to? So we end up with 4/3 times 1 plus t to the 3/4. And then we have minus 4/3, don't we? Okay. So everything I wrote here is the answer to that thing above. But now I need to actually take the limit, okay? So let's now take the limit. This is going to equal the limit as t goes to infinity of 4/3 times 1 plus t to the 3/4 minus 4/3. So if you let this guy go to infinity, that guy is going to go to infinity. So the whole thing is equal to infinity. So what do we say? The integral diverges. The integral diverges. Okay, so this is how we would approach this type of problem. Let's do another example. Let's do the integral from negative infinity to 1 of 2 to the r dr. So what is the definition of this? Don't forget to write it as a limit. It's extremely important. we're doing the limit as t goes to negative infinity, and then this goes from t to 1. And we have 2 to the r dr. So I'm actually, again, going to do this below. I know that this is what I need to integrate first. So what is the integral from t to 1 of 2 to the r dr going to equal? So what is the antiderivative of 2 to the r? The antiderivative of 2 to the r is actually 2 to the r divided by ln of 2. Okay? So that would be the antiderivative, and we're going from t to 1. So if we plug in 1 first, we get 2 over ln of 2 minus, and if we plug in t, we get 2 to the t divided by ln of 2. So again, everything you see here is going to get replaced above. And so this becomes the limit as t goes to negative infinity of 2 over ln of 2 minus 2 to the t over ln of 2. So what does 2 to the t look like as t goes to negative infinity? I want you to think about that. What is something to the power of negative infinity? Isn't that the same thing as 1 over 2 to the power of infinity? So actually what's happening here, and let's kind of, let me do this as an aside here, right? But what you're actually looking at is if you're doing 2 to the negative infinity, that's like 1 over 2 to the infinity, which equals 0. Now, I don't want you to write that on your paper because remember, writing stuff like 2 to the infinity doesn't actually make sense. Okay, you can't take a number to the infinity power. We're talking about limits here, but I wanted to sort of I wanted to justify why this limit actually goes to 0. And so the answer is 2 over ln of 2. Okay. So what does that mean? We would say the integral converges to 2 over ln of 2. So this is the kind of terminology that you're going to use when it comes to improper integrals. Okay, you're going to say whether it converges or diverges, and then you're going to say what it converges or diverges to. Sorry, what it converges to. If it diverges, you don't say it diverges to something. Diverge means it doesn't equal anything, right? Okay, let's do another example. Let's look at number 3. We're going to do the integral from negative infinity to infinity this time of x cubed e to the negative x to the 4th dx. Now again, we actually see that this is an improper integral, but what's special about this one is that we have an infinity on the top and the bottom. So what I said to do in the earlier step is we need to break this up into 2 pieces. We can go from negative infinity to 0 of x cubed e to the negative x 4th dx plus, and then we can go from 0 to infinity of x cubed e to the negative x to the 4th dx. And I'm going to call this guy I1, and I'm going to call this guy I2. Now, I want you to understand something, okay? The one on the left is equal to the sum of these two, but only if they both converge, right? Remember what I said in the rules before. I said if either one diverges, then the one on the left does also. So I can actually do either one of these. Let's go ahead and do I2 first. If this one diverges, I'm not even going to do I1. I'm just going to say that it diverges and we're done. Okay? And I can call this guy I if I want to refer to it easier later, okay? So let's look at I2. I2 is, of course, equal to this guy that I wrote down earlier, which I'm going to write as a limit. Remember, this is the limit as t goes to infinity of 0 to t x cubed e to the negative x to the fourth dx. Okay. So now what? Again, I'm going to do this integral and I'm going to do that separately. So let me try to do that over here. What would the integral from 0 to t of x cubed e to the negative x to the fourth dx look like? I'm going to let u equal negative, well, should I let u equal negative x to the fourth or just x to the fourth? It doesn't really matter. So I'm going to let u equal x to the fourth. So then du is equal to 4x cubed dx, or 1/4 du is equal to x cubed dx. So then this is going to equal 1/4, and then I'm integrating, and so I end up with e to the negative u du, right? What am I integrating from? Well, if I actually plug in t, I get t to the fourth. So what I'm doing is I'm plugging these guys in for x, right? And if I plug 0 in for x, I end up getting 0. So now I'm integrating from 0 to t to the fourth. What's that integral going to be? Well, the integral of e to the negative u is just negative e to the negative u. So I get negative 1/4 e to the negative u, and I'm going from 0 to t to the fourth. So that's going to equal negative 1/4 times e to the negative t to the fourth, and then I'm going to end up with a plus just because I'm minusing a negative. And if I plug in e to the 0, I get 1, so I just get 1/4. Let me make a little more room here since that line kind of took away my space here, right? So I'm going to write the limit as t goes to infinity, and then I'm going to write in what I just wrote, which is negative 1/4 e to the negative t to the fourth, and then plus 1/4, right? So what's going to happen as I let t go to infinity here? Well, remember, exponents come first. So infinity to the fourth power is basically infinity, but then we have a negative in front. So what's e to the negative infinity? Just like the problem before, this guy goes to 0. And so I actually get that this is equal to 1/4. So what just happened? I got a value for I2. I2 is equal to 1/4, which means I do actually have to calculate I1. Now, that might seem like a lot of work that I have to do another integral here. However, I don't have to do it from scratch because I already did the antiderivative, right? The antiderivative isn't going to change. All that's going to change is what I plug in at the end. Okay, so the only difference now is that I have the t. Let's write this down, okay? So what is I1 going to be, remember? I1, now I'm going from negative infinity to 0 of x cubed e to the negative x to the fourth dx, which is the same as the limit as t goes to infinity, negative infinity, of t to 0 x cubed e to the negative x to the fourth dx. So here's the thing, right? I don't have to do this from scratch because I did the exact integral before, didn't I? Except I didn't go from t to 0. Where did I go from over here? Over here I went from 0 to t. And so the only difference is that I'm going to get the negative of the answer I got over here, right? I'm going to get the negative of that. So it's going to be 1/4. So I'm basically just going to swap the two signs. So I get 1/4 e to the negative t to the fourth minus, right, 1/4. And now I have to send t to negative infinity. If you take negative infinity to the fourth power, you get infinity, and then you're doing e to the negative of that, and so this is still going to go to 0. So the answer is negative 1/4. And so, if we go back, I1 is equal to negative 1/4. So then what does I equal? So I is going to equal negative 1/4. So negative, let's write this down, I1 plus I2 is negative 1/4 plus 1/4, which is 0. So we could say I converges to 0. Okay. Again, if either one had diverged, then we would not have to do the other, right? But since they both converged, we added the two answers up, and that's what that gives us. If the part right here confused you about how I did this kind of in my head, you don't have to do that. You could just integrate it again from scratch, but just understand that the only difference between this integral and the one we did before was the fact that I'm going from t to 0 instead of 0 to t. So it's good to just understand that that's going to be the negative. One's going to be the negative of the other. Okay, the next thing I'm going to say is a cool result. It's actually a nice, interesting questions. So this will be our number 4. The question is, for what values of p does this integral converge? Does it always diverge? Does it converge? Or what this problem is implying is that maybe the power of p matters. Maybe if it's a particular p, it actually is going to converge versus diverge. So let's figure out what happens. So we get that this integral, what I'm going to do is I'm going to rewrite it this way. We know that this is the same thing. Let me actually back up here. We know that this is the same thing as sending t to infinity. And so I'm going to do this part separately, okay? So let's start with what happens if p is equal to 1. So Let's do that. What happens if p is equal to 1? So if p is equal to 1, then this means we have the integral from 1 to t of 1 over x dx. Notice I left the p out because I'm assuming p is 1. So this is like case 1, right? This is going to equal the natural log of x, and we're going from t to 1, and that's just the natural log of the absolute value of t, right? Because the natural log of 1 is 0, which means that the limit as t goes to infinity of the natural log of t is infinity. And so this means that it diverges. Okay, so we know that if p is 1, it diverges. So we're going to make the assumption, suppose p is not 1. So suppose p is not 1. So the integral is actually the limit as t goes to infinity of 1 to t of x to the negative p, right? I'm going to write it as x to the negative p dx. And so since p is not 1, we know we can use the power rule to do this, right? That's how you integrate that. So it's going to equal the limit as t goes to infinity of, we're going to add 1 to the exponent and then divide by that exponent, right? And we're going from 1 to t. So what is this going to equal? Well, what I can do here is I can actually, well, let me write it this way. Limit as t goes to infinity of, if I plug in t, I get t to the negative p plus 1 over negative p plus 1 minus, and then if I plug in 1, I just get 1 over negative p plus 1. What I'm actually going to do now is I'm going to pull out the 1 over 1 minus p, that's the denominator. And so I'm now doing the limit as t goes to infinity of t to the 1 minus p minus 1. There are now two cases here, right? I'm assuming that p is not 1, right? So what happens if p, so if p is greater than 1, then this means that we get the following. So this guy that we had above is equal, so p is bigger than 1. So what I'm going to do is I'm going to write it this way. Negative 1 over p minus 1, limit as t goes to infinity of 1 over t to the p minus 1, minus 1. So if p is larger than 1, then that means I'm doing 1 over infinity to a positive power, right? And infinity to any positive power is infinity. Or sorry, yeah, so we have infinity in the denominator and it's 1 over infinity. So what that means is that guy goes to 0, doesn't it? This guy goes to 0. And so the answer is just negative 1 over p minus 1 times negative 1, right? Because I have this times this entire limit, right? And so if I multiply it out, I end up with 1 over p minus 1. In other words, it converges. What about if p is less than 1? If p is less than 1, then that means what we have up there equals 1 over 1 minus p times, so this is the limit that we have. We now have infinity to a positive power, which goes to infinity This guy goes to infinity, so this equals infinity. In other words, it diverges. And so we're left with a conclusion, right? We now know that it converges when p is greater than 1, and it diverges for all other p's. And so let's write this down as our conclusion. This means that the integral from 1 to infinity of 1 over x to the p dx converges if p is greater than 1 and diverges if p is less than or equal to 1. Okay, so that's what we get for our answer. Now, we've seen enough examples, I think, for the infinite integrals. So remember we said that was type 1. So now let's talk about type 2. Type 2 is called discontinuous integrals. So let's write this down. A type 2 improper integral is a definite integral that has a discontinuity on a to b, where a is the lower limit of the integral and b is the upper limit of the integral. Okay, so that is what a type 2 improper integral is. So again, what we're basically saying, so e.g., we're integrating from a to b of f of x dx, but f is discontinuous somewhere on a to b. So this is like what we talked about at the very beginning of this lesson. Remember, I wrote down that integral and I said, is any of this valid? And we said no. That's because we had a discontinuity in there, right? And that's what we are talking about now, that type of integral. So we need to define this. So what is this going to mean, first of all? Okay, so it depends on where f is continuous. So first, let's suppose, so definition, if f is discontinuous so if f is discontinuous at b, then how are we going to define the integral from a to b of f of x dx? So b is the bad value, right? You can look at b at the top. You can think maybe the function explodes right there. Maybe it goes to infinity there. It's got an asymptote, something like that. How are we going to figure this out? Just like before, what we're going to do is we are instead going to take a limit. So let's think about what that limit would be. So what we're doing is we're replacing that bad value with a t. And now t is going to approach b. But we need to be very specific. We're not just approaching b, we're approaching b from the left, right? Because we're going from a to b. So just to give you guys a picture of this, let's say that this was a and this is b. And let's say we've got an asymptote there. So what we are talking about is something like this. And maybe we have our t right there. So what we're saying is that t is going to approach b, but you notice it's only approaching from the right, from the left. Okay, what's happening on the right is irrelevant. It might not even approach the same number. But we're going from a to b, and so only from the left matters. Okay, so that is the definition of what happens when the discontinuity is at b. So let's do the other case. So if f is discontinuous at a, then how are we going to solve a problem like this? So it's going to be the exact same thing, right? Except now t is going to approach a. But from which side? Well, of course, we're going from a to b. So we're talking about the limit as t approaches a from the right. Of that integral. Okay? So if f is discontinuous at a, this is what we're going to do. And if we were to draw a picture of this, it's this very similar idea to the one before. So if this is a, and this is b, and this is where our asymptote is, then our function might do something like that, right? And then we have so this is what we're talking about, right? We're approaching from the right. In other words, we're assuming that t is something bigger than a as we do this limit. Okay. Finally, what happens if the discontinuity happens somewhere in the middle? So let's write it this way. If f is discontinuous at c, where c is somewhere between a and b, then we have the following relationship. This is going to seem familiar to you guys. Instead of going from a to b of f of x dx, we're going to go from a to c f of x dx plus c to a of f of x. Sorry, not c to a. We're going to write c to b of f of x dx. Okay, so this should look very familiar to you. We did this in the case of infinity. So the point is, if the bad value occurs in the middle, what you want to do is you want to split it up there and then calculate both pieces similarly, okay? So let's just say this. If both, so I forgot to say something on the previous page, okay? So let me just say if these limits exist, we say the integral converges. And if not, it diverges. Okay, I forgot to write that down, but it's just like the problems, just like the type 1, okay? So I'm just going to say for type 2, okay, this is true. Now, for coming back to where we were here, I'm going to say if both integrals on the right converge, then so does the left integral, and it converges to their sum. If either integral on the right diverges, then so does the one on the left. Okay, so let me go ahead and draw a picture of this for you guys to try to visualize this, okay? So now what we're saying is that maybe our discontinuity happens somewhere in the middle, right? And so what we're saying is that we need to do both pieces individually. So maybe here it'll go to infinity, but, you know, something like this, right? This guy, we approach that line and we see if it equals something finite. And then on the left, that guy approaches that way. And our C is right here. And so what we're trying to see is, does this guy get finite? It gets finite only if both sides are finite. If either side goes to infinity, then the whole thing does. We cannot proceed any further. Okay. All right, let's try some examples here. So let's start with number 5. We're doing the integral from 2 to 3 of 1 over the square root of 3 minus x dx. Okay. So what do? Well, first we need to identify that there is a discontinuity, right? And if you notice something, plugging in x equals 3 gives you a 0 in the denominator. So we know that it's actually discontinuous at 3. That's our bad value. So this is going to equal, we need to use a limit to do it. This is going to equal the limit as t goes to 3 from the left of the integral from 2 to t of 1 over the square root of 3 minus x dx. So what does this become? Well, before we take an antiderivative of this, or let me just do this separately like I usually do. So I'm going to do this integral separately, and then I'm going to take the limit. So that guy, I'm going to write this as 3 minus x to the negative 1/2, right? That's how we can take the antiderivative here. So the antiderivative of this guy we're going to do using the power rule. So it's 2 times 3 minus x to the 1/2. And we're going from 2 to t, right? Because, oh, I do have to also divide by -1, right? Divide by the slope, because we have a -1 slope in there. And so what's this going to become? So this is going to become, if I plug in t, I get 3 minus t to the 1/2 minus, and then if I minus, it becomes a plus because it's already negative. And if I plug in 2, but 3 minus 2 is 1, 1 to the 1/2 is 1. And so this actually becomes -2 square root of 3 minus t plus 2. And so this guy is the same as this guy up here, right? And so I can go ahead and now take its limit. So I'm going to do the limit as t goes to 3 from the left of this guy that I got below. So what happens if I take the limit as t goes to 3 from the left? Then I know that that radical goes to 0, doesn't it? Because I end up with a 3 minus 3 under the radical. So this guy goes to 0. And so we get 2. So what do we say about this integral? The integral converges to 2. Okay. All right. By the way, before I move on, we notice that these problems can be a little tricky, right? Because you may not even notice there's a discontinuity if you're not paying attention. So this is why it's you have to be very observant when doing these problems. I'll just put it that way. Okay. Okay, let's try another one. Okay, so number 6. We're going to do the integral from 6 to 8 of 4 over x minus 6 cubed dx. Okay, pay close attention, and you'll notice that there is a discontinuity, right? Think about it. Where does this function not exist or is undefined? It's undefined here, so it's actually discontinuous at 6, right? Because if you plug in 6, you divide by 0. So we write it this way. We're going to do the limit as t goes to 6 from the right, and then we're going to integrate from t to 8 of 4 times, I'm going to write it this way, x minus 6 to the negative 3 dx. And so what I'm going to do is I'm going to do this integral separately like I've been doing. So let's see what the integral from t to 8 of this guy is. So I know that I can use the power rule for this, right? If I add 1 to the exponent, I get to the negative 2, and then I divide by negative 2. So that just gives me negative 2, and then x minus 6 to the negative 2. And I'm going from t to 8. So if I plug in 8, I get negative 2 times 2 to the negative 2, right? And then plus 2 times t minus 6 to the negative 2. But what's negative 2 times 2 to the negative 2? Well, 2 to the negative 2 is the same thing as dividing by 2 squared. So that's the same thing as negative 2 over 4 plus 2 over t minus 6 squared. Or I could just write it like this. Negative 1/2 plus 2 times t minus 6. Oh, sorry. I like it the other way better. Over t minus 6 squared. Okay. All right, so everything that we have here, this is that integral. So I'm going to now take the limit. So this is going to equal the limit as t goes to 6 from the right of negative 1/2 plus 2 over t minus 6 squared. So I want you to think about what happens as t goes to 6 from the right. It actually isn't going to end up mattering because we're squaring it. It doesn't matter if what we're squaring is slightly positive or slightly negative, because if you plug in t going to 6 from the right, then that means it's a little bit bigger than 6, and so the guy on the bottom is a little bit bigger than 0. And so in other words, we end up with this. Oh, sorry, I already took the limit, right? So it's going to end up being negative 1/2 plus, so what happens here? This guy goes to 0 from the right. And so that goes to infinity. And so this whole answer is infinity. So in other words, the integral diverges. Okay, be careful when you do limits. Just remember that if a denominator goes to 0 and it's always positive, then of course it's got to go to positive infinity. Okay. Let's do another one. This will be number 7. Let's do the one that I posed at the very beginning of the lesson, now that we understand the approach. So we're going to do the integral from 0 to 3 of 1 over x minus 1. Now, this is extremely easy to miss the problem here, right? It's easy to miss the fact that we have a discontinuity inside, because if you try 0 or 3, so if you try both 0 and 3, both of those things work fine if you plug them in, right? The thing that's bad, though, is we have a discontinuity at 1. And 1 is between 0 and 3, isn't it? So that's why this is a problem. And so we know we're going to have to split this up. We need to go from 0 to 1 plus 1 to 3. So let's go ahead and give these guys names. I'm going to call this integral I. I'm going to call this integral I1, and I'm going to call this integral I2. So let's do these one at a time. Which one do we want to do first? Oh, you'll notice, by the way, that this guy has a bad value up here, and this guy has the bad value down there, right? So just to point that out, you split it up at the bad value. So I'm going to go ahead and start with I1 this time. Why not? So remember, I can write it this way. I can go t approaching 1, this time from the left, and I have the integral of 0 to t, 1 over x minus 1 dx, right? So let's do that integral down here. If I do the integral from 0 to t of 1 over x minus 1 dx, this is equal to the natural log of x minus 1, and I'm going from 0 to t. And so this is going to equal the natural log of t minus 1 minus the natural log of the absolute value of negative 1 is 1. And so the natural log of that is 0. So this is all you get. I'll just write it this way so you could see. So that's just this. And so I just need to do the limit as t goes to 1 from the left of the natural log of t minus 1. So what happens as you plug this in? As you plug in 1 from the left, 1 minus 1 is 0. You get a really tiny negative number. However, because of the absolute value, it's positive, right? So the inside goes to 0. So what does the natural log approach? This entire thing approaches negative infinity. So let me remind you guys of what natural log looks like. Doesn't natural log look like this? And so if you're essentially taking the ln of 0 here, right? And so that's what we're saying, that this goes down forever as you approach to the left. So what does this mean? I'll say I diverges since I1 diverges. Again, guys, coming back up here, if any of these two integrals, this guy or this guy, if any of them diverge, then the left does also. And that's exactly what happened. We tried I1 and it diverged. Okay, so let me do one more thing here. One more example. I want to do an interesting case here. So what if we can't find the antiderivative exactly? We have something called the comparison test for integrals. So the comparison test for integrals. The comparison test for integrals says the following. So suppose 0 is less than or equal to f of x, which is less than or equal to g of x. When x is bigger than some constant. If this integral diverges, then this integral also diverges. So what are we saying here? We're saying that if the area under f diverges as you go to infinity, then the area under g must also, because g is bigger than f. That's what this is saying. So if g itself is too hard to calculate, you could just calculate a smaller function, and if that guy diverges, then so does g. Now, what else does it say? Well, we can also say the opposite. If the integral from a to infinity of g of x dx, so if the bigger guy converges, then the smaller guy also converges. Okay? So this is extremely useful when you're trying to figure out information about a function, an integral of a function, but you cannot actually compute it. You can look at something that you know is bigger or smaller, and that might be able to give you information. Okay? So we're ready to do the last example here. I think we're on number 8. Show that the integral from 0 to infinity of e to the negative x squared dx converges. So we have a problem. The problem is we cannot take the antiderivative of that. So problem, the integral of e to the negative x squared dx is not elementary. And remember, we discussed what that means. If it's not elementary, it means it's impossible to write down an antiderivative of this as a function, right? Just in function notation or whatever. So we need to look at this in an indirect way. Instead, what we're going to do is the following, okay? So as x gets large, right? So would we agree that x is smaller than x squared? That's true as long as we're bigger than 1. So actually, what I want to do is actually, instead of going from 0 to infinity, let me actually go from 1 to infinity. I think this will make the problem more straightforward if I just do this integral instead. So x is less than x squared, isn't it? When you square something, it becomes bigger. So this means that if you multiply both sides by negative, that negative x is bigger than negative x squared. So if that's bigger, then that means that take e to the power of that, and that's also bigger than e to the negative x squared. So why is this good? So what I just showed, and obviously we know that that's positive, so what I want to do is I want to write it this way. 0 is smaller than this, which is smaller than this. So since I found something that is bigger, e to the negative x, why don't I go ahead and calculate this? What I hope is that this converges, because if so, then I can say the smaller guy converges also. So what does this equal? This is equal to the limit as t goes to infinity of the integral from 1 to t of e to the negative x dx. Now, why is this better? This is a better integral to do, right? Because it's actually easy to integrate, unlike the other one, which was impossible. So what is this going to equal? This is the limit as t goes to infinity. You know what, actually, let me do this work on the next page, okay? Because I'm running out of space here. So I'm going to do this integral on the next page. So I'm going to integrate 1 to t, e to the negative x dx. The antiderivative of that is negative e to the negative x, and I'm going from 1 to t. So this becomes negative e to the negative t plus e to the negative 1. So now I'm going to go ahead and take the limit. Oh, let me actually write it this way too. This is what I get, right? Negative 1 over e to the t plus 1 over e. negative 1 over e to the t plus 1 over e. So if you send t to infinity, this guy goes to 0, and so the whole thing equals 1 over e. So this implies that this integral of e to the negative x dx converges. So what does this mean? I can say that the smaller guy converges as well. So by the comparison test, this integral e to the negative x squared dx also converges. Now you may wonder, what does it converge to? We actually don't know, right? The theorem does not tell us what something converges to. It just says that if something bigger converges, then the smaller one does also. And that's what we needed to show, right? All we needed to show was that that guy converges. Now, you're not going to see any problems on the homework that are this difficult. However, the reason I wanted to do the comparison test for integrals is that there is going to be a challenge problem that references this. It's going to be in the next set of challenge problems, not the ones for chapter 7, but the ones for chapters 8 and 9. Okay, so this will be a good thing to keep in mind as you move forward. Okay, guys, so that is it for this lesson. Again, the big takeaway here is remember that we have two types of improper integrals, right? We've got the ones where we have a discontinuity at the top or the bottom, or we have the ones where we have an infinity on the top or a negative infinity on the bottom. Okay? That is it for this lesson. Thank you so much for watching and hope it was helpful.